Hello everyone. So in this lecture we're going to be talking about the periodic table, how it's actually organized, and characteristics of or properties of actual elements based on their periods and groups. Remember again please that periods are rows and groups are columns. Okay, so the big organization of the periodic table is metals, nonmetals, and metalloids. So if you look at this schematic here in front of you, everything, if you draw a staircase between boron, aluminum, silicon, germanium, astatine, antimony, tellurium, polonium, so on and so forth. It's actually arsenic. This is astatine. What actually happens, folks, is you can see that everything to the left of that are actually metals. Everything to the right of that are nonmetals, and please note that hydrogen is actually a nonmetal, and some elements in between that staircase division is actually called metalloids or semi-metals. Okay, FYI, metals are solid at room temperature, except for mercury. Mercury is actually a liquid at room temperature. That's the only exception. And then the metals actually occupy all phases of matter. So any of the non-metals can actually be, in this case, solid, liquid, or gases at room temperature. Okay, an example is bromine. Bromine is actually, in this case, if you want to think about it, bromine is actually a crystal at room temperature. What happened to my cursor? Oxygen is actually in this case, a gas at room temperature, and iodine is actually a liquid at room temperature. Okay, and they actually can also exist at crystals as well. Iodine can also exist as crystals at room temperature as well. Okay, so nonmetals occupy all three general phases of matter: solids, liquid, or gas at room temperature. Metals, solids at room temperature except for mercury. Okay. Metals also conduct electricity. What that means to say is if I give you an iron, a 6-foot piece of metal, if I put a live electrical current on one end and you touch the other end, you're going to get a shock. Okay. Whereas if I give you, obviously, a long piece of a non-metal, okay, what happens is if I put an electric current on one end, you will not feel any current on the other end. Okay, so that's a very, very generalized thing. These things are shiny, dull. Okay, so general characteristics of metals, nonmetals, and metalloids. The periodic table can further be classified into groups here. Group 1 are called alkali metals. Group 2 are called alkaline earth metals. You guys can read this. Okay, Pnictogens 15. Group 15, that's actually also called the nitrogen group. Group 16 is called the chalcogens or the oxygen group. Halogens, group 17. And the noble gases is group 18. Okay. Transition metals are the D block elements, and the lanthanides and actinides are the F block, if you recall from your electron configuration. Okay. This is very important. Every single group have similar characteristics, have similar chemical and physical properties. Okay? An example is the alkali metals and the alkaline earth metals. These two groups, the reason why they're called alkali is because if you treat them with water, they actually will create a compound that is actually basic or alkaline. All right? Now, so that's one thing. Now, why do we care about this? Well, again, there are actually trends that you can actually look at when you're looking at the periodic table. So 4 of the things that we're going to be talking about periodic trends is ionization energy, electron affinity, electronegativity, and atomic radius. Okay, so we're going to start with the easiest one first, atomic radius. So if you go up, and if you go to the right, you have a smaller atomic radius, which means to say that if you go down in a group or left in a period, you will actually have an increasing atomic radius. And why is that? Well, let's think about this now. If we go to a periodic table, if we compare sodium and argon, sodium is number 11, argon is number 18. Argon will have what we consider to be a smaller atomic radius and sodium will have a bigger atomic radius. Why? Well, atomic radius, if you want to think about it, folks, is the relationship between the number of electrons and the number of protons. Okay? Recall that in the earliest lecture that the actual radius or the actual size of the atomic cloud is dependent upon the number of electrons. The more electrons you have, generally speaking, the bigger the electron cloud, and therefore the bigger the atomic radius. However, you need to consider that electrons are negatively charged. And we know for a fact that in the nucleus, there resides a subatomic particle known as protons, which are positively charged. Okay? So even though sodium or argon has more electrons than sodium, argon, the neutral argon atom has 18 electrons and the neutral sodium atom has 11 electrons. The argon atom also has 18 protons. So the protons actually in this case have a bigger exerts a bigger attractive force towards the electrons, and that is why the atomic cloud, the atomic radius, is actually compressed in argon as compared to sodium. So between sodium and argon, again, just remember that as you go left, you have a bigger atomic radius. Sodium will have a bigger atomic radius, and argon will have a bigger atomic radius. It's the same as you go down. Okay, so if you go down, lithium will have a smaller atomic radius than francium. Francium will have a bigger atomic radius, and that should be, in this case, intuitive because francium has 87, the neutral francium anyway, has 87 electrons. So obviously 87 electrons is way, 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 way more than 3 electrons. Okay? So that is the trends for atomic radius. Now, a very different thing, however, is these 3 other properties: ionization energy, electron affinity, electronegativity. Okay? And these 3 properties are directly or primarily based on the number of electrons or electron configuration. All right? And this is where I'm going to introduce you to a law or a rule called the octet rule, or in this case, the duet rule. So I'm going to go back. So in this case, we're going to compare the structure of the electron configuration of oxygen and lithium in this case. So oxygen in electron configuration is 1s2, 2s2, 2p4. Okay. And I'm going to actually do sodium, folks. So sodium in this case is similar to that. It's sodium. This is taking forever. 1s2, 2s2. This is painfully slow. I'm very, very sorry. 2p6. And 3s1. Okay. Now, there is a most stable electron configuration, and the most stable electron configuration, folks, is actually in this case exemplified by the noble gases: helium, neon, argon, krypton, xenon, radon, and oganesson. In this case, if you noticed, if I write the electron configuration of neon, we might as well compare neon to this, guys. Neon, folks, is similar to this, guys. It's 1s2, 2s2, 2p6, 2p6. Okay? Why? So this is called the octet rule because if you look at the electron configuration of neon, in the valence electrons of neon, again, the valence electron is the highest energy level. So there's a 2s and 2p, and if you look at the exponents, 2 plus 6 equals 8. This is the most stable electron configuration. Now, both oxygen and sodium, folks, because of their distance. Now, FYI, sodium can actually become like neon, which is the most stable electron configuration, or can become like helium. It can actually go backwards or forwards. But what happens, folks, is just by distance, if you want to think about it, if it wants to become like helium, it has to go backwards 6 times. If it wants to go forward, it needs to go forward 2 times. So oxygen then, in order for it to, in this case, have its most stable configuration, it would like to add 2 electrons. All right. Sodium then, if it wants to become like neon, again, sodium has 2 choices. It can become like argon or neon, but again, neon is closest backwards. It would like to get rid of the 3s1. And note that if oxygen gains 2 electrons and sodium gets rid of 1 electron, what happens to the valence electrons? 2 plus 6, oxygen will now have 8 valence electrons. Minus 1, 2 plus 6, now sodium now has an electron configuration of similar to neon. So at this point, if oxygen gains 2, sodium loses 1, both of them now look like neon in terms of electronic configuration. And that is the most stable conformation, electron conformation for oxygen and sodium. And that is why sometimes it's called the octet rule. Octet basically means 8. Okay? Now, so there are properties. So if you go back to this rule again, now why is it, now if you look at this one, folks, if you go right and you go up, you have a higher ionization energy, higher electron affinity, and higher electronegativity. One exception to this rule, folks, is electronegativity and electron affinity, folks, is the noble gases already have their fill. So in this case, they don't exhibit any electronegativity or electron affinity, okay? So just as an FYI, very quickly for that one. So think about sodium again. So if we go back to this thing, let's compare the ionization energy between this case sodium. Let's actually do the same row, lithium and oxygen. Which one will have the highest ionization energy? Well, oxygen. Okay, ionization energy is the property or the amount of energy required to remove an electron. Okay, oxygen, folks, wants to gain an electron. So in order for you to remove an electron from someone who wants to keep it, it's going to require a higher amount of energy. Lithium, on the other hand, it wants to lose an electron. So it should be obvious to everyone that because in this case, then the ionization energy for lithium is going to be way, way, way lower than the ionization energy for oxygen. Okay? So again, in a row or a period, whichever one is to the left is going to have a lower ionization energy. Whichever one is going to be to the right is going to have the highest ionization energy. Okay? Now we also can talk about, in this case, the trend going up. So folks, lithium will have a higher ionization energy than sodium. Now there's a complicated theory to this, and the reason why lithium has only 3 electrons. So therefore these electrons are closest to the nucleus. Okay, so therefore the protons are pulling harder at those electrons. Now sodium has 11 electrons, they're further away from the nucleus, so therefore the electron, the 3s1 electron in sodium actually experience less of an attraction to the nucleus. That is why lithium will have a higher ionization energy compared to sodium. Electronegativity trans is the same. Electronegativity trans is actually, again, please remember that the noble gases are not involved in that one because they do not wish to gain or they already have perfect electrons, so they don't wish to gain or lose electrons. Folks, fluorine has the highest electronegativity. Why is that? Because of its, again, electron configuration, right? So in this case, between fluorine and nitrogen, fluorine would want really, it's so close to neon, so therefore its thirst for an electron is way, way, way higher than nitrogen's thirst for an electron, if you want to think about it that way. So again, folks, the trends is quite straightforward because this table is actually going to be given to you. Just remember that if the elements are arranged in a group, the higher element will always have the highest ionization energy, highest electron affinity, and the highest electronegativity.